Hello, everyone. My name is Dmytro. I work at Facebook, and I am one of the leads of PyTorch project there. So actually, today I'm going to talk about scaling innovation process in AI, and specifically like some of their kind of findings and tools which we built at Facebook and together with community around PyTorch to facilitate that. So specifically, we're going to talk about challenges of bringing new ideas to production and how like PyTorch deep learning platform kind of helps with that. And we're going to go through three particular aspects of creating and scaling AI models around programming languages, scaling distributed training, and touch a little bit about lifting hardware limitations. So at Facebook, we have a lot of AI models in critical business applications, and they're often at core of our products. And if you look at kind of innovation process, like usually advances in AI research are driven by applied research in industry or some academia research advances. And historically, there has been this kind of process of transitioning new ideas to deployment. And it often takes quite some time. You need to determine your approach and prepare the data and build and train new model. Often your tools don't align, so you have to like re-implement it maybe several times and tune, and only then deploy and kind of roll it out at scale. And some of the things which like Reza was just talking about is basically how to accelerate this process. So we also believe that like closing this gap and kind of accelerating the innovation, bringing new ideas is a huge opportunity to basically increase positive impact of AI models in the world. And it's particularly essential since we depend more and more on these models and quickly deploying them as business critical, both for applications such as content moderation or healthcare or generally security and stuff like that. So if you look at kind of why this process is challenging, there are several kind of aspects which you can highlight. One of them is system performance. So as previous speakers talked, training sophisticated models takes time and data sets are growing. So you actually really want to get everything out of underlying hardware. And related skill issue to that is scaling, because often tackling larger model complexity data sets, you need to go distribute it and push it to the next level. Or if you're talking about deployment stuff, models need to run on a lot of different environments from cloud to the edge and embedded systems. One particular challenge which kind of matters actually a lot, and I think sometimes people don't often highlight so much, is like ease of experimentation. Because if you think about like one of the most critical resources in kind of advancing state of the art is actually researchers' time. And basically speeding up rate with which you can come up with new ideas, implement them, try them out, and probably discard a lot of them, but discover the good ones is actually really critical for innovation speed. And it's also like really hard. I mean, this field is pretty much new and has been revolutionized in like last decade. So it's really hard to predict what exact model patterns or compute patterns are going to be available in the future. So it's important to structure platforms in very kind of modular way so it's easy to use and reconfigure as new ideas arise. There's always this temptation to create two different platforms for research and production needs, which would strike different trade-offs on this balance. But it comes with a challenge that it often takes quite some time to like take the same idea and like re-implement it multiple times. So it's actually, ideally, we want to target a single platform which can cover the whole spectrum of use cases and basically be tunable without having to like drop it and go to different tools. So with PyTorch, we basically try to address some of these challenges, and I'm going to talk about a little bit kind of philosophy and like practical tools for doing so. So if I kind of summarize, at the core of PyTorch lies this idea that like AI model development process, it's effectively a programming exercise. And we can learn a lot from like kind of traditional way people design and like apply best practices for software and frameworks building. And it turns out that kind of following these principles allows us to build pretty good user-friendly platform that both encourages innovations and allows enough flexibility to kind of adapt to new ideas in different environments. More specifically, I would probably highlight three principles. One of them is building modular components with least amount of friction. You can think of it as kind of like Unix philosophy application, basically building a lot of interoperable components which do one job well, instead of like one monolithic solution which tries to be configured for everything. And similarly, PyTorch doesn't have one rigid prescribed way of doing things. It basically gives you, as a developer, a lot of control for implementing stuff. So if you have a crazy idea, it's very likely that you can take existing pieces and basically combine them in novel ways with relatively little code and developer iteration time. Of course, there are best practices for kind of scaling AI and best models. So we do provide packages on top which incorporate these practices and provide turnkey solutions. A lot of the solutions are actually built by community. But the kind of important property of the platform is like if these high-level APIs don't suit you, it's very easy to kind of drop the level down and try to tweak whatever details you are interested in, whether you're doing research or actually some applied applications. So I think like some of the folks here probably use PyTorch. I've seen a bunch of PyTorch hoodies. But for those who didn't, basically it's deep learning kind of framework and platform, which is, as I said, is a collection of components. At its very core, it's pretty much efficient tensor library, similar to NumPy, which of course comes with GPU acceleration and automatic gradients. So whatever code you write, you can get differentiation on top of it. Comes with standard building blocks for building your neural networks, such as standard layers library and optimizer packages and data loaders, recipes for distributed training, and also as we kind of go more towards production iteration, it has kind of C++ runtime for embedded or at-scale applications, and even some like APIs for if you don't want to use Python at all. And there are a lot of other components, but what's particularly like makes this kind of platform popular and gain popularity is there's a lot of cutting-edge research models which are available. So if you just search GitHub for latest papers, very likely you're going to find like either first or second implementation being in PyTorch, which is great, so it's easy to pick it up and try it out. And of course, because of, I mean, there's Py in the name, one of the strengths is basically connection with Python ecosystem. So it's very easy to kind of cross the boundary, or like don't have this boundary at all, and like leverage to all of Python scientific ecosystem, being it like data loading, visualization, or other types of algorithm, etc. So combination of this kind of design principles which I mentioned made actually PyTorch extremely popular in deep learning research community, despite the project being like about 2 years old and like stable release being only like half a year ago. It's actually one of the top tools mentioned in like recent, like last year's iClear or NeurIPS papers, which is great. And even more, we kind of seen like these tools being used in a lot of fields which are outside of traditional deep learning. In fact, there are folks like using PyTorch in like particle physics research at CERN or in computational chemistry on drug discovery, which actually proves that like a lot of tools get adopted if they're good. There's a pretty strong community around PyTorch, which both kind of builds different tools and packages for different subdomains, from like NLP to probabilistic programming to like system components to make the system better. And also this community involves a lot of like strong partners, both from academia and industry, and often like community projects actually drive big parts of the development. A lot of kind of academic institutions release new groundbreaking research implemented PyTorch, which is great, and also like some of their kind of like industry partners also like innovate on systems side. For example, like a lot of submissions from NVIDIA for MLPerf mentioned earlier were actually done using PyTorch, and they're contributing back to this stuff, which is awesome. So kind of overall, PyTorch provides like you tools for rapid experimentation and deployment, and it's open accessible platform which allows developers to both push state-of-the-art in research and kind of quickly scale and bring that to business needs. So now let's actually look at those aspects which enable this in some of the approaches. First one I'm actually going to talk about is more like programming languages perspective. And if you kind of been following deep learning frameworks for like past several years, there is this like long-time trade-off between different design principles. One of them is called like imperative or eager, which basically treats framework as a library embedded in host programming language, such as Python or Swift or something like that, or Julia. Each time like user runs some statements, it's very intuitive. Statements immediately produces results. Declarative approach basically starts with exposing user to some other like domain-specific language, where you need to construct representation in your program and only then kind of explicitly run and optimize it on some specialized like virtual machine. I mean, both of these approaches have their pros and cons, and it's actually not exact dichotomy. For example, in imperative mode, assuming that you have actually control on the underlying language or compiler, it's possible to extract deferred representation and like optimize it for new hardware and do all the tricks. Whereas with imperative, you kind of always force the user to start with this representation, which makes it easier to optimize, but makes it harder developer experience. So with PyTorch, like kind of originally from the beginning of the project, one of the strengths was actually fully embracing like imperative or eager programming model. That's why it basically feels just as using another Python library. You fully embed it in host programming language, so if you know Python, you know how it works. If you write your code, you can get the gradients using autograd, whatever that code is doing. Since it's native Python, you can easily interface with your other favorite tools you've been using. And of course, you can use like favorite debugger of all time, which is print statement. If you want to use some crazy obscure Python library, you certainly can. And actually, like a lot of fundamentally new models, especially like in research, usually start with this way with like really hacky code where you stitch together different libraries and like try to basically figure out whether some idea works or not. However, it also comes with downsides. You are coupled to Python, which basically prevents you from running environments where Python interpreter is not available. Also, Python interpreter has a global lock, so it's not very friendly for cloud environments if you're trying to run multi-threaded. And of course, like adapting to new hardware sometimes becomes a challenge. So that's why in the past year, and it's kind of part of 1.0 release back in December, we built another model for kind of another mode for PyTorch called script mode, which effectively provides you a subset of Python, which is usually people use for building neural networks. So it has all the like standard neural networks library, tensors, all you would expect from PyTorch, and also traditional language features such as like if statements, loops, user-defined types, etc. It somewhat restricts like dynamic crazy behavior of Python, which actually makes it like makes Python difficult to optimize, but allows you to enable a lot of good stuff. We still believe that like kind of imperative mode and like just writing programs is the right way for most users to start coding, kind of like start developing their models. And for the subset of models which are kind of need to scale up for crazy distributed training or maybe have need to be deployed in kind of edge devices, stuff like that, PyTorch JIT basically provides like this tools for taking originally written imperative mode and converting it to Torch script, so more optimizations are possible. Specifically, there are two tools kind of developed there. One of them is tracing, and another one is scripting, so I'm going to talk about it in more details. So tracing is actually a pretty simple thing. So if you have your straight line model, you pretty much can run it in Python and kind of record in the background every kind of tensor operation and every kind of neural network layer which got executed. All you need to do is effectively just provide sample inputs for your models. This works great for majority actually of vision models which don't have control flow, but if you have control flow in your model, then and you apply tracing, you most likely like end up with something which you don't want. For example, if you have like simple RNN with a for loop there, and you run an example input, you're going to end up with like unrolled RNN for that lens, which might be fine for optimization, but you only can run on sequences of a fixed lens, which is usually not what you want. So kind of explicit script mode basically takes a different approach, and especially it's useful for models which have control flow. So effectively, you can think of it as an annotation which makes PyTorch compile a subset of Python code. All you need to do is basically just put an annotation on your function. We're going to parse the source code, like basically compile to its internal representation. So you can see like loops and control structures, everything of that gets supported. Control flow gets preserved to this, and unlike kind of pure declarative perspective, it still feels like a programming experience. You are still writing just a subset of Python. You are not writing like a different programming language. Basically, if you put these tools together, it kind of really it's really important to like focus on programmers and like developer experience. Effectively, there are several kind of things which we found important to making this workflow of transition and kind of engineering smooth. One of them is really focusing on incrementality. So basically, we allow to like mix chunks of regular Python code and Torch script code and tracing and kind of script modules together, so you can still run them in our program and like do this transition gradually on function by function or module by module level. Usually there is only small pieces of your model which are performance critical and need some tricks, and you can keep the rest of it the way you want it without constraints. Also, Torch script kind of follows the design of following explicitly a subset of Python. So for things which it supports, it matches Python semantics pretty much directly. So if something isn't working, then you can just remove this annotation and use your regular like PDB and Python tooling to debug what's going on without changing your debug workload. And of course, I mean like just regular kind of programming languages principles such as like don't pay attention to error messages and stuff like that are also important in this case. So great, we have like tooling for extracting kind of program representation from Python. Like how is it actually useful? Like why do we build it? There are, I would say, like two main kind of buckets of applications. One of them is ability to do whole program optimizations and kind of ahead of time analysis, which is what kind of traditional compilers has been doing for quite a while. And in fact, it becomes like more and more important as modern hardware gets faster and faster. Even like if you look at like GPUs, often like CPU becomes a bottleneck for driving that, so you kind of want to fuse multiple operations together and do a lot of that for user under the hood. Otherwise, you might have like super expensive GPU sitting on your desk being bottlenecked by just CPU feeding commands for this. And similarly, there are like a lot of other kind of opportunities for optimization compilers can do. For example, you can exploit memory layout of your tensors and kind of reorder them behind the back by doing different blocking and padding. So you minimize data movement, use your caches better, and effectively your synths runs faster. And of course, as kind of more and crazier hardware gets available, ability to actually directly generate machine code for the target platform effectively simplifies adoption of new architectures. So instead of implementing all the like hundreds of operations for every architecture by hand, you can generate reasonably good code, or sometimes even better code automatically. Of course, from user experience perspective, similar to traditional compilers, it's paramount to pay attention to kind of developer experience and preserve semantics, so all of these transformations happen transparently for you. And like by enabling some optimization, you don't suddenly get like wrong results. So that's one of the things we focus a lot. And on kind of on backend compiler side, kind of more on code generation sense, a lot of these things actually in development, we have like integrations ongoing with like several kind of backend side compilers. One of them, some of them is like Glow or TVM or XLA. So there's like a prototype running on Google Cloud with TPUs, which is cool. Some preview versions of that are available. Kind of second reason why you might want to extract kind of deferred representation of your program is basically running without Python. Python is really taken off like a kind of data science ecosystem quite a bit. It's really great for prototyping your models. It's actually, in many cases, just fine to do training of your models if you do things right. But it often becomes a bottleneck if you're trying to write models with very small layers, or especially when you're trying to put it in like your like data center scale inference, where you're kind of forced to run several processes because Python interpreter can run only one command at a time. And similarly, like if you're trying to run on mobile phone, which Facebook will do a lot, for example, for client-side applications, you're kind of forced not to use Python interpreter at all. So with Torch script, the models can be effectively saved in the archive and loaded from C++ API directly without any need to depend on Python interpreter. And also like usually you can do it only for inference portion of the model, which is usually much smaller than all the training tricks incorporated there. In fact, as we kind of were building this functionality, we realized that like in many kind of deployment cases, like C++ usually is a good language for implementing that because it's kind of system language and has a good interfaces with a lot of other languages we are trying to build. And in fact, like PyTorch core is actually built in C++, so we ended up basically exposing a lot of low-level kind of tensor level, like kind of linear different layers APIs in C++, which makes it easier to integrate your model in your target applications. And if you, for example, have some image preprocessing which you want to code it there, you can still use the same libraries and pretty much the same APIs. The cool part is like actually this API is almost identical. So if you just copy paste some code and try to like replace, like add autos and semicolons, usually it kind of works. We build it mostly for like inference kind of deployments, but to kind of highlight the points from earlier about building self-contained components which work well, often it leads to like unanticipated use cases. And in fact, like some of the research teams like utilize this kind of PyTorch C++ API actually to write training loops and like do the whole training. Because for example, they're building like StarCraft reinforcement learning agents, and their like integration with game environment actually makes it hard to use Python. So that kind of wraps up the programming languages part. I want to talk a little bit about like distributed training and some of the kind of applying these approaches to it. So I mean, first of all, why distributed training is important is because like going to more compute resources and being able to scale to larger data sets is usually leads to like more accurate and better models. Second important reason is actually makes iteration faster. Like if you want to wait for your model to train for 1 hour instead of 1 week, you're going to try more ideas and probably discover better ideas. However, distributed training usually doesn't come for free. It requires a lot of kind of communication and thinking about distributed systems. And it's not only like a systems problem, it's a very often kind of leaks into training algorithm to think about like how do you do wedge norm in distributed training, how do you control this batch size, some of the things which they was talking about earlier in the morning. Impact of that is, however, is really huge. Like as in one example from like last year, some of the work we did at Facebook, we basically took like weakly supervised data set from Instagram images, which like 3-something billion images, and 17,000 hashtags, pretty much trained standard like ResNext architecture on it. Just one weakly supervised labels, and for comparison, like ImageNet training data set is usually around like 1 million images. And despite those labels being like very noisy and kind of semi-supervised, we actually were able to achieve with the same model like 2% higher like test accuracy on ImageNet, just from like pre-training on a huge amount of kind of images, and obviously utilizing a lot of kind of hardware in the process. And it also requires both hardware and kind of training algorithm tricks. So from PyTorch as a kind of deep learning framework perspective, we want to give user power to like leverage this distributed training techniques for like efficiency and faster iteration. And we do it actually on 2 levels. So like on level, we provide like scale building blocks to algorithm authors to utilize. So since like if you're trying to build your distributed algorithm, you probably need like service discovery and like communication primitives similar to like collectives in MPI. And they work smoothly with the REST PyTorch ecosystem, so you can like send tensors around and like do gradients and stuff like that. Of course, for most kind of typical strategies, such as distributed data parallel, where you just replicate your model across workers and like exchange the gradients, we provide a standard recipes for kind of typical training strategy, which incorporate best practices. However, if something basically doesn't work, it's easy to drop off for you as an algorithm author and try to tweak details. So on communication primitive sides, it's pretty much, you can think of it as like similar to MPI collectives library, which kind of integrates with the rest of either Python or C++ PyTorch ecosystem. On backend, it would use actual communication libraries such as Glue or Nickel from NVIDIA and stuff like that. And those are the primitives which you usually need to build your training algorithm if you're trying to do research in this area. If you're training your like regular computer vision NLP model, usually majority of them follow the strategy of distributed data parallel, which is basically just replicates your model across workers and shards the data between them. And from user perspective, for this high-level API, pretty much all you need is like add 2 lines of Python, wrap your model, spawn out workers on whatever cluster system you use, and you're pretty much done. And in particular, this API is like, again, carefully designed to like encourage flexibility. So we don't actually take control over you. You're still writing your own training loop. So if you want to tweak around with like learning rate schedules or do some crazy things, it's very easy for you to do, kind of still taking only a little bit of control from you, what is necessary for system-wise, but leaving a lot of that to the user. And of course, like under the hood, like data parallelism has a lot of, probably the most robust approach for kind of training distributedly, especially for like CNN architectures. Like optimizing that kind of happens on 2 levels. The main operation usually is called all reduce because you sharded your training, like your mini batch across multiple workers. Each of them computed like parameter updates and gradients, and now you need to like sum them up together and distribute results to everybody. Luckily, this operation has been optimized in like HPC computing for pretty much several decades, so there's a lot to learn from that. And there are a lot of tricks about how to like utilize different topology and do like local reduction stuff like that, and actually like work from, for example, Nickel also helps there a lot. There are also some things which we need to take care and kind of we incorporate in distributed data parallel from like framework perspective. The simplest thing is as you're doing the backwards pass of your model, some of the gradients already become available, so you can start doing communication in the background to overlap it together. What ended up also happening is like if a lot of your parameters are actually very small, then initiating separate exchanges is also expensive, so it makes sense to kind of bucket them behind the back and like exchange smaller number of blocks. And if you apply all those tricks well, then effectively like the profile you want to see in your utilization is basically compute and communication streams perfectly overlapping, and no one is waiting for each other. These techniques work really well. Is like one example for like fair-seq model, which is like fairly complex like sequence-to-sequence machine translation models, which was kind of like developed in research and now is actually like used for Facebook machine translation. This is like even slightly harder problems than usual like CNN models because amount of parameters compared to computation is actually higher, and also like the mini batches on different workers they usually have different sizes because it's like sequence modeling task. And in fact, like applying these techniques and going from like 1 to 16 boxes with each of the 8 GPUs, you actually see like almost like 6x improvement in speed up, which is really good in this case, and especially for like somebody trying to do experimentation with this model, going from like 3 hours to half an hour is a big deal. And specifically those kind of tricks of incorporating the best kind of exchange on framework level actually bring another like 20% performance gain in this case. So we talk a little bit about kind of software perspective of how to unblock innovation and iteration speed. I want to a little bit touch about some of the hardware challenges and like how we kind of basically think about it. So in some sense, it's a little bit complementary to like earlier talks about customized hardware. So I want to take a different example. If you actually look from what's driven like recent deep learning craze and like innovation, there are 3 main components. One of them is innovation in algorithm space. So we know much better now how to train those models and tune them. And I wish we knew even better. A lot of these advances come from more compute power, which got available in the recent years. And of course, there's huge data sets, kind of probably should have been listed as the first reason for that. So you can kind of have much better tools to work on data and basically analyze it and feed it to the training. The tricky thing is that better algorithms and more compute are often adults from like developer experience perspective, because if you're trying to kind of squeeze out more compute and more machines, usually it means going distributed, or it means doing specialized machines, etc., which are harder to program. Like it's harder to think about distributed system compared to a single box. Whereas from algorithm innovation, you usually want to have like it's much easier to program like single-threaded or single machine program. That's all the programming which we like to do. So there's this challenge kind of how to, especially when you're trying to unblock experimentation, try new ideas, like before the scaling phase, what kind of hardware kind of system, what kind of type of servers would enable this innovation faster? And effectively, you kind of want all of it, right? You want single box programming environment, but also a lot of compute, a lot of interconnect, and a lot of memory capacity and bandwidth. So at Facebook, we've been actually building our own like server designs for the past 8 years, kind of starting more from like web applications, etc. We actually open source all of those like hardware, like server design, data center design through Open Compute project. So, and there are like other partners which utilize this. That also applies to kind of ML server training hardware. In fact, we've gone through several generations of kind of servers which we use and which are fully open source designed in Open Compute project, from kind of like early ad hoc solutions to like latest kind of big basin Volta, which has like 8 NVIDIA Volta GPUs and basically delivers you a lot of performance. So at recent Open Compute Summit, which was actually just a few weeks ago, we talked a little bit about targeting diverse training workloads. And one of the challenges which we kind of see at Facebook a lot is that for many models in personalization and ranking, they actually have huge number of parameters. So they would have like embedding tables or stuff like that with like hundreds of billions of parameters, which require huge memory capacity and also huge memory bandwidth, just in addition to regular kind of compute-heavy deep learning parts. So we basically set out to build a system from standard building blocks, which would be relatively cheaper, so which would kind of unblock this experimentation. It has 2 components. One of them is Angel's Landing, which is effectively 8-socket CPU chassis, which for memory-intensive part of the problem, because it still uses regular DRAM for kind of being cheaper and more affordable, but because of using 8 sockets, it actually delivers enough memory bandwidth for you to experiment with. Second component there is basically a chassis for accelerator portion for like GPUs or training ASICs called Emerald Spool. This kind of like common form factor which we are kind of working with industry partners to kind of standardize. It also supports multiple kind of communication technologies to deliver interconnect for that all reduce step. Putting them together, you effectively have this kind of modular system called Zion, which you can also partition between different applications and like take on the number of GPUs if you want. It can basically have GPUs and can have in the future training ASICs as well. And what's important is like such hardware setup pretty much allows teams to experiment with larger categories of models, more like traditional deep learning models, also the ones with higher memory bandwidth and kind of capacity pressure, while still using kind of programming environment close to like single machine or for prototyping algorithms, because even if you don't optimize completely out of it, you still will run fairly fast. So it's kind of like system counterpart of like a lot of kind of software flexibility, which I talked about earlier from like PyTorch design. So far we basically covered kind of several topics which help you to kind of accelerate innovation in, this in the field of AI. So if you want to learn more, please go to like pytorch.org and Facebook AI to more details about it. I think I am just on time, but maybe I can take one or two questions.
Yeah, thank you, Dmytro. Yeah, thank you. Let's thank Dmytro. And we have time for one question, and then we should switch. Okay, well, there we go.
Thank you. So I wanted to ask you, what happens to the Caffe2 APIs?
Yeah, so the history of that, we actually kind of had two projects, Caffe2 and PyTorch, which are now united together. So Caffe2 APIs are still available in this package. We don't plan to like develop them much further, front-end wise. A lot of actually compute technologies which are part of Caffe2 now are part of this unified PyTorch project. So from API perspective, I would encourage you to basically use kind of PyTorch APIs, but a lot of compute pieces inside that actually been there. If you use Caffe2 today, it will continue working for whatever future. So yeah.
All right, thanks. Thank you, Dmytro.